So here we have the diesel cycle example from the presentation. Just a few things to keep in mind. Here's the ideal diesel cycle: isentropic compression, constant pressure heat addition, isentropic expansion, and constant volume heat rejection. The displacement volume, the volume at bottom dead center minus the volume at top dead center, so V1 minus V2. Compression ratio, volume 1 divided by volume 2, and cutoff ratio, volume 3 divided by volume 2. So here we go with the example. It says we have a displacement volume of 5.6 liters. I'm going to leave that for just a second. So if I convert that to meters cubed, that'll be 0.0056 meters cubed. 1,000 liters in a meter cubed. So process within each cylinder in the engine are modeled with the air standard diesel cycle. Cutoff ratio is 2.4. I'll just write it as that, cutoff. Told us some conditions at the beginning of compression, so that would be time 1, P1 95 kilopascals, T1 27 degrees or 300 Kelvin, and the initial volume 6 liters, 0.006 meters cubed. We want to know the net work in kilojoules. So that would be a capital W. Power in kilowatts. That would be the rate of work. And the so this is at 1500 RPM. And then the thermal efficiency is our other question. Okay. This is 1500, we'll put cycles per minute. Because in the ideal diesel cycle, we get power out every time we execute this cycle. In the actual diesel cycle, we're only getting power out every other cycle, because every other cycle is also just getting the products out and getting more air and fuel in. And so this would correspond to the power we would get from this engine at 3000 RPM in a standard diesel cycle engine, a real diesel cycle. So alright, we're looking for network, power, and efficiency. So maybe let's start with the network. It's going to be Qin minus Q out. Really, it's the work done from process 2-3 and 3-4, the area under that curve, minus the area under the curve 1-2. But we can take a big picture view of this engine. We have Q in, we have work net, and we have Q out. It's easier to evaluate Q in and Q out and solve that for work net. So that's the equation we have here, Q in and Q out, because they only occur for one process. There's Q in here, and there's Q out there. Alright, so we're looking for Q in and Q out, so we're going to go to process 2-3. It's a constant pressure heat addition process. So that's kind of like a freely moving piston cylinder. Even though this isn't freely moving, it's constant pressure. So we could think of it as that. So we have Q in, we have boundary work because the volume is going to get bigger during the process 2-3, equals the change in energy of the system. So mass times the final would be 3, the initial would be 2. Constant pressure boundary work, we can bring it over here, take the integral of PdV, combine it, and eventually we would end up with H3 minus H2. So all we need are H2 and H3, and we'll be set. So let's work on those. So we have all the conditions at 1. We have the cutoff ratio, the displacement volume, and volume 1. So if we can get the cutoff ratio, we can use the fact that it's isentropic from 1 to 2 in order to get T2, which will tell us H2. Then we can use the cutoff ratio to get to T3, which will tell us H3, which will get us Qn. So let's get going on that.